This video contains the notes for section 5.8, which is about rectilinear motion. What does that mean? That means motion back and forth along a straight line, or in other words, one-dimensional motion. Later in the year, we will use parametric or vector-defined functions to analyze two-dimensional motion. Right now, we'll just talk about one. And also, once we learn how to do integrals in the next chapter, we'll have an even better way of dealing with this. But we'll introduce the topic now and see what we can do just with derivatives. So let's say we have a position function which might be called, our book uses S for position functions, S of t. Sometimes in the AP test, the College Board will use X of t, like that, to mean you're moving back and forth like along an x-axis just in one dimension. So those are interchangeable. So we've got a position function, S of t. Well, what do we know about derivatives? What's the derivative of position? Well, velocity is the derivative of position. You want to think about that in terms of slope. Velocity is defined to be how far you went, a change in position over a change in time. Change in position over change in time, that's the slope of this. So velocity function would be the derivative of position. And acceleration, well, what is acceleration after all? Isn't it the change, your velocity changing, like either speeding up or slowing down? So the second derivative of position would be equal to the first derivative of velocity, which is acceleration. So if you're given a position function, it's very easy to find velocity and acceleration from that. You just take derivatives. This should seem familiar. If you're in any kind of physics class this year, you've already talked about this pretty extensively. Okay, so what do we do with that? Well, let's just talk about a couple other things that we need here. Definitions. First of all, speed. Velocity, notice there's no absolute value signs or anything. This could be positive or negative. Positive would mean we were moving to the right, and negative velocity would mean we were moving to the left on our one-dimensional number line. Just like position can be positive or negative on the number line, so can velocity, so can acceleration. But speed is an important concept. Speed is the absolute value of velocity. And of course your car, for example, has a speedometer, not a velocimeter or something like that. In other words, your speedometer in your car only ever gives you positive values. It doesn't care about what direction you're going. It just gives you positive numbers. It's the absolute value of your velocity. And that means that for our common sense, that something moving in a straight line is speeding up. In other words, to our eye, it appears to be going faster as time goes by if the velocity and acceleration have the same sign, both positive or both negative. Something appears to be speeding up if the velocity and acceleration have the same sign. If they're both positive, that means you're going this way and you're adding, your acceleration is how much you're adding to your velocity. So it would appear that you're getting faster and faster that way. But if they're both negative, it means you're moving in this direction to the left, and your acceleration, since acceleration is negative, you're subtracting from your velocity, which makes the absolute value of it get bigger in the negative direction. Likewise, something is slowing down if velocity and acceleration have opposite signs. You could think of that as being sort of like a wind in your face effect. If your velocity is this way, but your acceleration is fighting against you, that's going to make it seem like you're slowing down. Likewise, if your velocity is negative, but your acceleration is positive, those two things are fighting against each other, and it will appear that you are slowing down. Okay, so let's do an example and see what we can figure out. So let's say we are given a position function s of t is equal to 2t cubed minus 21t squared plus 60t plus 3. You might just think what you know about polynomial functions. How many times can this thing possibly turn around? Well, a cubic function has, if we graph it like this, has this sort of shape. So this thing, I think, since it's positive here, could be something that's moving this way, turns around, and then turns around again, right? If it were quadratic, I think quadratics just have one turnaround, right? One turnaround. Cubics, this could be going like this. Okay, so we're expecting two possible turnarounds. All right, let's do the following. Let's find the position, velocity, and acceleration at time 2. Well, we have the position function, so that would just be s of 2. That would be equal to 2 times 2 cubed minus 21 is 2 squared plus 60 times 2 plus 3. And probably you'd have a calculator for this problem. That's 16 minus 84 plus 120 plus 3, if I haven't made any mistakes there. So that's, let's see, 20 minus 80 would be 40 plus 1. That's 6. I think that's 55. Yes? Perhaps. Yes. Velocity. Well, we haven't found the derivative of this yet. The derivative, let me put a t there. The derivative of this would be 6t squared minus 42t plus 60. So the velocity at time 2 would be 6 times 2 squared minus 42 times 2 plus 60, which is 24 minus 84, negative 60 plus 60, which is 0. The velocity is 0 there. What does that mean? Well, it means that that must be one of the turnaround points, right? A place where the velocity is 0 is probably a place where the velocity is going from positive to negative or negative to positive. So I think we just found one of those. Might be able to use that later. And the acceleration function, the derivative of velocity, that's 12t minus 42. And at 2, that's equal to 24 minus 42, which is, I believe, negative 18. We weren't told any like meters, seconds, whatever, so we can leave these as unitless. But if position, for example, were in meters and time were in seconds, this would just be meters, this would be meters per second, and this would be meters per second squared. Okay? Now what else can we do? Given the same function here, let's find the intervals of speeding up and slowing down. So during what time periods is the particle speeding up? When is it slowing down? Now speeding is about the agreement of the velocity and the acceleration and their signs. So what we need to do is find where both the velocity function and the acceleration function are equal to 0, in other words, where they're changing sign, and then set up a kind of a double number line situation here. And we're only interested in times that are greater than or equal to 0. Usually we start counting at 0, so don't care about negative stuff. Okay, so let's take our velocity function and set it equal to 0. Right? We want to know where it's turning around. So 6t squared minus 42t plus 60 equals 0. Factor out a 6. And that looks like it factors into t minus 2 and t minus 5. So the velocity is 0 at 2 seconds and 5 seconds, or whatever time units these are. Okay, now let's do the same thing. Let's set the acceleration equal to 0 and see where that changes sign. Acceleration is 12t minus 42 equals 0. And factoring out a 6 gives me 2t minus 7. So it looks like t would be equal to 7/2. So the acceleration is 0 at 7/2. Okay, so I show what I mean by the double number line. So I didn't put an arrow on this end because we're starting at 0 and I don't care about anything below that. So here's time 0. On the top of the number line, I'm going to put places where velocity is equal to 0, and on the bottom of the number line, I'll put places where the acceleration is 0. So first of all, velocity is 0 at 2 and 5. Right? Notice I only made those marks go up. Those are my velocities. And acceleration is equal to 0 at 7/2 or 3.5. Right here. Okay, now play the number line game. Here, between 0 and 2, at a value like 1, say, what's the sign of the velocity? If I plug 1 in here, I get negative times a negative, or positive. A number like 3, in between 2 and 5, I have positive, negative. That would be negative. And at a value above 5, like 6, they're both positive. Now, in the bottom, my acceleration, looking over here, if I pick a value in between 0 and 3.5, like 2, plug it in here, I get 2 times 2, 4 minus 7 is negative. And then up here, put something like 5, then it's positive up here. Okay, so in between 0 and 2, my velocity is positive, my acceleration is negative. So that means from time 0 to 2, we are, since these are fighting against each other, it's slowing down. Between 2 and 3.5, the acceleration is negative, right? And the velocity is also negative, both negative in here. That means we're speeding up. If the signs agree, we're speeding up. From time 3.5 to 5, negative and positive, so I'm slowing down. And finally, from 5 on up, we're speeding up again. Okay? Now, one more thing. I'm still going to use that same function. Let's say we were asked to find the displacement and the total distance traveled. Those are going to be different from time 0 to time 7. Now, displacement is easy. To find displacement, the definition of displacement is just your position at time 2 minus your position at time 1. What happened in between? It does not matter. When we're finding displacement, we don't care. Displacement is literally, if you ignore everything that happened in between, how far away was the starting point from the end point. So in this case, my position function, I'll just rewrite it here real quickly, was 2t cubed minus 21t squared plus 60t plus 3. So my displacement from time 0 to time 7 would be s of 7 minus s of 0. In other words, where you are at 7 minus where you are at 0. And let's see, I might cheat and use my calculator for the s of 7. So that's going to be 2 times 7 cubed minus 21 times 7 squared plus 60 times 7 plus 3. It's 80. And s of 0 is 3, so that's 77 units, whatever they are, meters, whatever our distance units are. And our total distance is a little bit trickier because if you live, let's say, I live about 15 miles away from the high school, so my displacement from the beginning of the day to the end of the day is 0 because my position is at home and at home, right? That would be 0. But the total distance I traveled is 30 miles, right? Nobody's going to argue with the fact that I went 15 miles south and then came 15 miles back north. So I did, in fact, put miles on my car, about 30 miles. But my displacement is 0 because I'm at the same place. So how do we find total distance? We have to find all the turnaround points, which is where the velocity is 0, right? If you're going to turn around, well, you turn around when your velocity is 0. If you're going south and we say that that's negative, and then you turn around and go north, that's positive, you have to cross over 0. So let's see if we can do that. We're looking for time 0 to time 7. So we actually have already done this. I'll just remind you. Here we found where the velocity was equal to 0. Happens at 2 and 5. So this is what we need to do. This should feel kind of like finding the absolute maximum and minimum of a function on a closed interval. We need to find what's my position when I started at 0, what's my position at time 2 when I turned around, what's my position at time 5, which is another turnaround, and what's my position at time 7. And then find how far I actually went in each one of those intervals. So s of 0, we already found that, that's 3, and while we're at it, we already found s of 7, that's 80. What's my position at 2? I think I found that here. It's 55. And what's my position at 5? I'll leave it for you to check, confirm that that's 28. So you can see I went forward, backward, and then forward again. So although from here to here my displacement is 77 units, I actually traveled further than that, and total distance traveled wants to take that into account. So when I went from 3 to 55, how far did I go? I went 52 units. When I went from 55 back to 28, how far did I go? I went 27 units. You might say, well, you went negative 27, but here we're interested in absolute values only, right? Actual distance. Distance, like speed, is always positive. Have you ever answered the question, how far is it from here to there with a negative number? No, you have not, because distance is always positive. Here to here, I went another 52. So what's my total distance traveled? 52 plus 52 is 104, so it's a 131 units. Notice that these numbers are not the same. If there's been any kind of turnaround point at all, these numbers will not be the same. Of course, if you only travel in one direction, then your displacement and your total distance traveled could certainly be the same if you never turn around. But if you do turn around, like we did twice here, then the total distance you travel will be greater than your displacement.